This invention is for a long telephoto lens that maintains good image quality while remaining telephoto even at close range. Invented by an SBIE Conradi Award recipient, I don't think you'll be disappointed by the elegant effectiveness of this invention. Lenses with long focal lengths, longer than the lens system itself, are telephoto. So what do? Close-ups and far away. In lens design jargon, they have a narrow field of view. This invention answers several design challenges, such as controlling the off-axis aberration at all object distances and focusing close-up with minimal lens travel. The lenses in this invention can move for focusing purposes, but this isn't a zoom lens. If the lens travel takes the lens through a large range of focal lengths, such that one extreme is wide angle and the other extreme is telephoto, then it would be a zoom lens, and then when zoomed out, a wide portion of the scene is reproduced on the 35mm film format located at the image plane. Telephoto prime lenses lack the zoom. They don't shift to the short focal lengths of wide-angle lenses. Photographers love them. Let's see how this one works. I'm going to simulate the embodiment in this figure. The first two elements are positive lenses made from crown glass. The third element is a negative flint glass, and the fourth is a positive flint glass. The last two elements are negative lenses made from crown glass, with the last element being a negative meniscus lens with its concave side facing the image. The exact location of the stop isn't specified. I'll start with it halfway between L3 and L4. Stop location doesn't influence effective focal length or paraxial magnification, but it does affect image quality. Lens element L6 is weaker than the others, but it keeps the off-axis aberrations, such as coma and astigmatism, small as the focus is adjusted. Although low-power lenses contribute very little spherical aberration, they can have more effect on coma, astigmatism, and Petzval. In the case of coma, L6 is simply canceling the small residual coma that remains after L5. And this weak meniscus lens still has plenty of lens power to be a reasonable field flattener. So what does it do again? A telephoto lens uses its long focal length to produce a close-up image, an image with higher magnification. This is as opposed to a wide-angle lens. A telephoto lens most certainly has a small field of view. This diagram implies that the image distance is different for telephoto and wide-angle cases, which would be impractical because the film would have to be moved for each setting. However, real telephoto and zoom lenses are made from several lens elements, and the effective focal length is adjusted by moving some but not all of the elements. This effectively moves the rear principal plane around in such a way that the image will always form on the same plane for all focal length settings. For the telephoto case, the principal plane must be in front of the first lens so that the effective focal length will be longer than the total track length. A telephoto prime lens is not an adjustable zoom lens. It's a permanently zoomed-in lens, but usually with a focus that is adjustable by moving some of the elements. This invention is about a lens that is always in the telephoto case. It doesn't zoom out to wide angle, but it does maintain telephoto focus over a very broad range of object distances. In a telephoto lens, the positive power is in front and the negative power is in the back. That's the case here with the first four elements forming a positive group. In some embodiments, the last lens is positive, but in all cases in this patent, the last two elements together form a negative group. The front positive group might be regarded as two positive lens groups separated by an aperture stop, and by adjusting the separation between L5 and L6, the back negative group has an adjustable negative effective focal length. The last element, L6, serves as an aberration corrector. The first five elements move as a group while lens 6 remains stationary relative to the image surface. The object distance that comes into focus varies from about 2.5 meters out to infinity as the front five lenses are moved over a travel distance of about only 11 millimeters. It'll be up to analysis to determine if the lens remains telephoto for all values of the lens separation. The example that I'll simulate is an approximately f3 lens able to focus on object distances ranging from 2.372 meters out to infinity. In doing so, the adjustable space in front of L6 varies from about 3.2 millimeters for an object at infinity to about 15 millimeters for the closest object. The size of the image frame given here is enough information to determine the field of view, and I'll come back to that in a minute. First, the lens prescription needs to be entered into the lens data editor of Optics Studio. The surface radii and thicknesses are entered along with the refractive indices and Abbe numbers. Let's check this design for 3 object distances. Using the software, I'll determine the appropriate spacing in front of L6, which in the lens data editor is surface number 11. That's why these V's for variable are after the entries in the multi-configuration editor. They're left as variables for the optimizer to figure out, and as a preview, these are the values that work. If you look at the bottom of the screen, the effective focal length and total track length for the current configuration are displayed. The ratio is the telephoto ratio, which as promised by the title of this patent is less than 1. The focal length changes only a small amount as the lens is focused on the range of object distances. As a result, the lens travel is also small, and thus the telephoto ratio is claimed to only change a little bit. We'll check that out. In our example embodiment, a lens forms an image on a 24 by 36 mm format. It's reasonable then to expect that the light arriving at the film forms a circle of radius 21.6 mm or larger. So the analysis will use an image height field definition with 21.6 mm as full field and 15.3 mm as the usual intermediate field. It's well known that lens patent embodiments are rarely optimized, and that's the case here with the 71 micron on-axis RMS spot radius for 6 meter object distance, and it's quite similar for a 2.3 meter object distance. The Wavefront plot covers a 1 mm range, at least at the outermost field, and reveals spherical aberration, some coma, astigmatism, and chromatic aberration. These play out in the Seidel coefficients. What can be learned from a table like this is the role of each surface in producing, or rather correcting for, aberrations. Spherical aberration is cancelled by surfaces with alternating positive and negative values. For example, surfaces 1 and 4 produce large positive spherical aberration, which is cancelled by the large negative of surface 5. The final negative meniscus lens element defined by surfaces 12 and 13 plays a particularly important role in off-axis aberrations. Both coma and field curvature are large before this element and are subsequently cancelled by it, and to a lesser extent the same is true for astigmatism. Managing the third-order Seidel aberrations of a negative meniscus and astigmat comes at the cost of distortion. The final element roughly doubles the distortion. The impact of distortion on image quality is more tangibly understood as a percent of the full image size, and at positive 2.75%, distortion may be small enough to evade detection by the human eye. Distortion is negative for the large field of view wide-angle lenses. Think about the extreme case of a fisheye lens, which exhibits extreme negative or barrel distortion. Telephoto lenses, on the other hand, have positive or pincushion distortion. The whole point of a telephoto lens is to clearly resolve a faraway object, giving some importance to the modulation transfer function. I've seen it stated that a good MTF target for a 35 mm film camera is 30% at 50 line pairs per millimeter. You might know some other target, but I'm going to see if this embodiment can be nudged into that performance. Any product being developed will likely have a budget for RMS wavefront error, and the lens design is allotted some small amount, perhaps a quarter of a wave. In high-precision applications, such as, for example, laser beam shaping, that budget allotment can be as small as 1/20th of a wave. Manufacturing tolerance will be a separate but larger part of the budget, but your simulated design needs to have an extremely small wavefront error, which, to add some confusion, is different in each field and wavelength. There are a few ways to view this performance in Optics Studio, one of which is the Wavefront Map. The RMS wavefront error averaged over the pupil for the on-axis field at the primary wavelength in configuration 1 is 3.9 waves. We'll see how close this gets to a quarter of a wave with a little optimization. And I did a little optimization on this embodiment to see that this patent indeed covers some outstanding telephoto lens designs. With an effective focal length of almost 200 millimeters, this is on the edge of being a super telephoto lens, usually considered to be those with a focal length greater than 200 millimeters. These are larger than most telephoto lenses, and because of the large entrance pupil diameter, in this case 60 millimeters, they're used for action and wildlife photography. The large entrance pupil diameter of long focal length lenses makes spherical aberration more difficult to eliminate. I constrained the object at infinity case, configuration 3, to a focal length of 200 millimeters as specified in the patent. The necessary focal lengths for the finite object distance is something that the optimizer will have to tell me. Line 4 shows the telephoto ratio for configuration 1, the case of the shortest object distance. It's important for the spot size to be small, so I used a spot size default merit function, but the contrast won't be very good unless I ask for good contrast. So I added all of these MTF operands, constrained by these operand greater than operands. And then this is repeated for the other two configurations below. With boundary conditions placed on all variable thicknesses, let's run local optimization, and a lens prescription results with a much smaller merit function. This lens invention works very well when optimized to your custom requirements. One other thing that I did when setting this up was I substituted the glass properties from the patent with closely matching real glasses. Something that I didn't do was allow the glass selections to float during optimization, which would have produced an even better outcome. The final negative meniscus lens element, surfaces 12 and 13, is still in the form of a negative meniscus, carrying out the very important role of aberration balancing. Overall, the aberrations were significantly improved by just a little bit of local optimization. The object of this invention was to keep the last lens element stationary with respect to the image surface. The first 5 elements are all fixed relative to one another, and the entire group of 5 moves as the thickness of surface 11 varies. This was the point of analyzing 3 different configurations for 3 different object distances. When the object is at infinity, the space between the last 2 lens elements is 2 millimeters. The effective focal length was 200 millimeters as set up in the merit function. The F number came out to 3.38 and the telephoto ratio is 0.878 less than 1. With the object located 6 meters out, the lens spacing is 5.6 millimeters as expected. The focal length is a little shorter and the total track length is a little longer by exactly the change in surface 11 thickness. At the closest object distance of 2.372 meters, the telephoto ratio is 0.985. So even at less than 2.5 meters, a telephoto focus is maintained. A telephoto prime lens and a zoom lens can be distinguished by the adjustable range of focal lengths. The focal length of a zoom lens is varied in order to adjust the magnification. The focal length of a telephoto prime lens is varied in order to move the object location. And this requires only a small range of focal length variations compared to a zoom lens. Rather than ranging from 70 to 190 microns, now the spot sizes are beginning to approach the diffraction limited value of 2.799 microns. This is the case across all 3 configurations, maybe with the largest field infinite object case perhaps still in need of a little more refinement. Distortion for all configurations is around positive 2.2%, but there's something else that we get from this. I had set up the lens using an image height field definition. This was to ensure that the light collected by the lens fills the detector. But to know the field of view angle then requires converting the field type to angle. Well, that's done automatically when plotting the distortion, since the plot is made as a function of field angle, which in this case is between 5.4 and 6 degrees. So close up or far away, the field of view is small. There's no wide angle configuration. This is a telephoto prime lens, not a zoom lens. If a photographer needs to change how the scene fills the detector, it will be necessary to move the camera closer to it or farther away from it. By using those MTF operands, the spot size was reduced while the contrast was significantly improved. The same is true for the 6 meter object distance, and the same for an infinite object distance. We'll need to take a look at the image after checking wavefront error. Maybe you recall that before optimizing, the RMS wavefront error for the closest object distance was about 3.9 waves. With optimization, it's a tiny 0.1 wave, easily meeting the optical design limit imposed by a system budget. It's also good for the 6 meter object distance and the infinite object distance. But these 3 plots were for the on-axis field only. Wavefront error does get a little worse for the off-axis field. In all of these cases, the ratio of RMS wavefront error to peak-to-valley wavefront error is between 2.7 and 5.6. Significant spherical aberration in coma would leave you with a larger ratio than that. This size of the ratio is indicative of simple focusing error and some astigmatism, but three different object distances all need to share the same image plane, so each configuration is undoubtedly slightly out of focus. Another way to look at wavefront error in Optics Studio is the simulated interferogram, which presents the result in a form that's more familiar to many users. But only the peak-to-valley wavefront error is shown explicitly in the interferogram information box, so I do prefer to view the wavefront map. When focused at infinity, there's probably very little interest in any part of the image being blurry. But when focused on a closer-in object, blurriness behind and in front of the object might even be a desirable artistic effect. A depth of field calculation reveals the range in front of and behind the point of optimal focus where the acceptable focus is also achieved. Approximating it with this expression for a thin lens, I'll estimate the maximum acceptable blur diameter for the closest 2,372 mm object distance as the same 17 microns that was simulated. The depth of field is then 16 mm. If instead we decide that the acceptable blur is 2 times the on-focus blur that we simulated, then the approximate depth of field would be 2 times larger, or 32 mm. Suppose I wanted to take a picture of this tree bud from 2.7 meters away. A depth of field of 16 mm would mean that the branches and twigs in the background will be blurry. If I back away and adjust the focus to 6 meters, the depth of field goes to 100 mm. If I step further away so that it's a faraway object, the depth of field in principle goes to infinity. So how does the image of a scene look through this lens? The relative illumination roll-off at the edges was actually better before optimizing. Generating this image was literally the last thing I did before my ZMAX license expired, and the next thing would have been to insert another operand in the merit function, either an RELI, relative illumination, or RANG, ray angle operand, along with an operand less than operand evaluated at the image surface to rein in some of this roll-off. The clear aperture of the last element did shrink by about 1 mm during optimization, accentuating the cosine to the fourth problem, but also indicating that there's room to improve it with the correct operands. And also designing for the smaller image format of a digital camera would result in a much more uniform illumination. But if the spot size is too large, or the contrast is too small, that's a bigger problem. But with this lens, the image quality comes out quite well. You can compare parts to the source image on the left. In both cases, you can see the cloud details in the mountaintops. If you look closely at the trees, you might notice that the fine details are a little less resolved in the simulated image. Before the late 1940s, this lens would have had poor performance because of Fresnel losses on the 12 optical surfaces. Additionally, multiple reflections would send light back to the film, leaving bright areas where there were none and even ghost images. Today, those effects are mitigated by anti-reflective coatings. So let's get a sense of how helpful that is. First, use the ghost focus generator in sequential mode. The results from each double bounce in the system are listed out. Only a few double bounces are likely to show up, with reasonably small spot sizes forming on the image surface. If the spot size is large, like say 28 mm, then the stray light is likely to be too dim. In this case, the smallest spot size was 6.6 mm for reflection first from surface 11 and then from surface 9. For each double bounce, a ZMX file is generated with a lens data editor inside of it. We're looking at the case of reflection first from surface 11, then from surface 9. The reflected light arrives at the image surface, making an RMS spot radius of 6.043 mm. Notice that the light emerging from the last glass surface is slightly diverging. The distance to the ghost focus is minus 348 mm, meaning that there's a virtual ghost image quite a ways in front of the first lens. Although what matters is the stray light reaching the detector, let's go ahead and see what this minus 348 means. The lens data editor created by the Ghost Focus Generator places mirrors on what was previously surfaces 11 and 9, with these mirrors ordered sequentially so that the previously numbered surface 9 reflects light that had been reflected back to it from the previously numbered surface 11. If I place a marginal ray height solve on the last glass surface, the diverging rays will be traced virtually back to the virtual ghost image. The end of the ray trace is in fact 348.1 millimeters in front of the image surface. So that's what distance to ghost focus means. Sequential mode Ghost Focus Generator gives some information about the main offending surfaces, but a non-sequential ray trace gives detailed information about the flux arriving on the image surface and where it comes from. So convert to non-sequential and look at the small detectors that are centered on each field. Well, I'll take the time to look at field number 1. The speckles outside the spot are stray light. Applying anti-reflection coatings to all of the surfaces cleans this up quite a bit. Interesting, the flux, or rather power, arriving on the detector nearly doubles, indicating just how much Fresnel loss is eliminated by the coatings. Anti-reflective coatings are key to this lens having good transmission with low contamination. The patent categorizes this invention as a sonar type of lens, which interestingly historically included 2 or more cemented surfaces and even filled in air spaces, such as after the second element, with glass in order to further reduce reflections. But the eventual introduction of anti-reflective coatings added more degrees of freedom by keeping Fresnel losses low while not having to cement surfaces. And you probably notice this lens doesn't include any joined surfaces. With 12 air glass interfaces, anti-reflective coatings are indeed quite necessary. I'll apply a filter that limits the traced rays to those that reach the big detector object 16 with the filter H16 and that are double bounced before arriving, that is ghost rays, or filter G0. The relative intensity of the ghost rays will be much smaller than the brightest image rays, which have a relative intensity of 1, so set the minimum relative intensity high enough that only 1 or 2 most intense ghost rays make it into the ray trace. If I set this too low, we'll see a lot of ghost rays and we won't know which are the most intense. A close-up shows one of these rays bouncing first off surface 6, then off surface 5. The other ray bounces first off surface 8, then off surface 5. Refresh the screen and 2 more ghosts are traced. One of them is the same as before, and the other one is another 8, then 5, suggesting that reflection off 8, then 5 is a likely source of light contamination. So apply anti-reflective coatings to surfaces 5, 6, and 8, and lower the minimum threshold from 3.4 times 10 to the negative 3 to 2.4 times 10 to the minus 3. Now there's a bounce off of surface 11. I'll add a coating to surface 11. Keep going, and going, and going. Here's the brightest ray at the 8 times 10 to the minus 4 threshold. Well, let's just give all of the lens surfaces anti-reflective coatings, and let's even add a lens tube, which I'll just make moderately reflective, only reflecting 5% of the light and scattering 85% of it into a Lambertian distribution. By reducing the ray intensity threshold to 1.5 times 10 to the minus 4, I find some additional stray light reflecting off of the tube. But that light might be blocked by the optomechanical components, a natural stray light shield. Speaking of optomechanics, this figure was included in the patent. The glass arrangement is different, but I think the point was to illustrate the optomechanics. The focusing ring typically found on telephoto prime lenses can be rotated in order to adjust the desired lens separation, which in this case is the spacing in front of the last element. Can you see how all but the last element move as a group as the housing tube is rotated on its threads? I hope you learned as much as I did tearing into this patent. Thanks for watching.